So in the last video we learned about shear and bending moment equations, and that we had to basically make some free body diagram like this that represented all these cuts and solve that free body diagram for the shear and the bending moment functions here, and then we would just plot them. But that got a bit tedious because with that method we would have to make a free body diagram for this section and a free body diagram that covers that last section. But there's actually a quicker way to figure out the shear and bending moment equations. And this is made possible because we have these relationships between W, our distributed loading, V, our shear, and M, our bending moment. And these relationships are this. My shear equation, my V as a function of x, is going to be the antiderivative of my distributed loading function. So remember, W is the distributed loading intensity. So for that one, that'd be really easy. That would just be W is equal to 300. And of course, it would be negative 300 because this W is acting downwards. So we would basically integrate this, and that would be our shear equation. I'm not going to show the derivation for these relationships. I'll have that in another video. In this one, I'm just going to show you these equations and how to use them to generate these V and M curves very quickly. And the other relationship is our bending moment equation is the antiderivative of the shear equation. So this is it. You'll take the antiderivative of the W equation, get your V, take the antiderivative of your V, and get your M. So, we'll get some experience with these new equations in a second. But let me just say a few things. So my book presents these equations using the definite integral. Remember, the definite integral is going to give you the change. It's going to give you a number. I like doing it using the indefinite integral because when you do an indefinite integral, you end up with an equation. Like that. And doing this indefinite integral is nice because with the equation, it gives you all the information of the curve. Rather than if you just do it with the definite integral, you just get a number here and you don't have the entire equation. Technically, you don't really have all the information at your disposal. So to do it this way, it'd be nice if you have your graphing calculator with you to assist you. It makes it really, really straightforward. So once you get really, really good with this stuff, you might be able to switch over to these and graph your V and M equations a lot faster. And we'll do this in some of the practice videos. But for just introducing this concept, we'll just do the indefinite integrals. So the antiderivative of my W is my V, and the antiderivative of my V is my M. A consequence of this is that the derivative of my V is my W, and the derivative of my M is my V. So just keep those in mind as well. So here are these new relationships, and we'll apply them to more quickly graph our V and M curves. So, same first step, we need to figure out our support reactions, A and B. I'll have a 1.5 times a 300 for the total force of this distributed load. Its distance will be half of that 1.5, which will be 0.75. And I can sum my moments about A here. And I can solve this equation to get my B. And I'll get a positive 312.5. And now I can do the sum of the forces in the y to find A. So I have A going up, I have this 450 going down, I have the 600 going down, and I have my 312.5 at B going up. We can solve that, and we'll figure out that A will equal a positive 737.5. Alright, so before we take the antiderivative of this W, we're going to want to determine the very first points on our V and M graph. And the reason we want to do this is that this is going to help us figure out our constant of integration. Whenever you take an antiderivative, you have that C. So these sort of initial conditions will allow us to figure out that C. So the way we're going to do that is I'm going to do a free-body diagram on basically the first cut we can, that x is equal to 0 cut. And what forces are acting on this cut? Well, I'm going to have the 737.5. I'm going to have my shear. And I'm going to have my internal bending moment. And don't forget our conventions here. I'm assuming these things to be positive, my V and my M. Now you may be wondering, wait, why didn't I draw part of the rectangular load right here on my little FBD? And the reason for that is, well, technically it is. Technically. Here's our W equal to 300 Newton meters. But remember, I have to times this W by a distance to get the force. And this distance right here is so tiny that when I times it by this 300, I basically get a 0. That's how tiny this dx is right here. So because of that, I can basically neglect the W acting on this. So with that being said, this is my free-body diagram at this very initial cut. So, quick sum forces in the y tells us that this V has to be a 737.5 going downwards. And remember, this is our positive direction here. So this is going to be positive shear. So I'm going to treat each one of our units here as 250. And that basically puts this 737 right around here. Just make sure you really get why this is positive shear here. Alright, so at x is equal to 0, my shear, that is to say my starting shear, is this positive 737.5. Now for my M here, well, in a sense we can take moments about this point here. Of course, the moment of V is going to be 0. This guy will have a moment arm, but this moment arm is so small such that when we multiply it by this force, it basically gets us 0 moment. So that's 0 as well. So because of this, my M at the beginning is 0. Now if I had some externally applied couple moment at this endpoint A, then of course it wouldn't be 0. But basically, since there is no externally applied couple moment at this x is equal to 0 start, my starting bending moment will be a 0. So here it is right there. Now to get into the good stuff. Let's make my W equation. Well, my W equation to start off with is this right here. So my W is equal to a constant 300, and I just got to remember that this is going to be negative because these forces are acting downwards. My V will equal the antiderivative of negative 300. with respect to x. And carrying out that antiderivative, we'll get that v is equal to negative 300x, and of course a plus c. And of course, my equation here isn't complete until we figure out the c. Well, no problem, because we know that at x is equal to 0, my v is equal to a positive 737. So plugging in a 0 here and a 737.5 into here allows me to figure out c. And doing that math, this is a 0, which means c will be a 737.5. Perfect. So this w here is valid from here to here. So same applies with my v equation. This v equation is happening. It gives us all the v's for all the x's from 0 to 1.5. So I can just graph that. So I'll just call this 1, 2, and 3. Our entire beam is of length 3 meters. So what I see here is a line. This is basically y is equal to mx plus b with a negative m here and with this starting point. So we know we're going to end up with something like this going on. And we know that this equation stops at 1.5, so we will be stopping around right here. The question is, do we stop over or under? Well, again, we have all the information we could ever need here. We can figure this out. We can just plug in 1.5 into this x, and we'll figure out what our v is. That'll be a positive 287.5. So that will be basically around right here. And of course, we'll have a line in between the two. So here's all my complete shear information here. Now I could take the antiderivative of this and figure out my bending moment from 0 to 1.5, but I'll just keep going with the shear. Now, notice that here we have one of those point loads. Now remember, we learned that a point load will cause one of these instantaneous shifts, up or down, of my v equation, or my v curve. And the way that I think about this is imagine here's this externally applied point load right here, the 600. And here is my positive internal shear. Because we have a lot of force pushing down, we're going to need less of this shear, less of this positive shear. And because we need less positive shear, this will be a downwards shift of our v, downwards by 600. So if I do 287.5 minus 600, I can find out where we end up after this instantaneous shift. That's 312.5 negative. So that'll be about here, I would say. So looking onwards, I don't see any w, which means w will equal 0. So of course we'll apply our equation again, that relationship. My v equation will equal the antiderivative of this w with respect to x. This w is basically going to be a 0, and the antiderivative of that really just means that v will equal some constant number. Remember, the reason for that is because if we take the derivative of a constant, we get 0. And we can figure out what this constant is, because at x is equal to 1.5, right where we left off here, my v is equal to that negative 312.5. And you may be asking, all right, wait, why isn't it 287.5? Well, it's 287.5 right before we hit that 600. At cuts right before the 600, we have this 287.5. Right after it, we have this negative 312. So since we're trying to figure out the v after the 600, we choose the negative 312 to figure out the c. So that's an easy one. Of course, our c has to be a negative 312.5. And notice that my w is equal to 0 follows basically until the end of the beam. So this v equation is valid until the end of the beam. And it's just going to be a horizontal line, a constant negative 312. Now, we're at the very end, so we gotta make sure we're getting to 0. So here is my beam, and here's this basically last cut at x is equal to 3. And I have this 312 point load, 312.5 point load at B being applied. So again, we come back to this idea. Here is basically my final V value at x is equal to 3. If we have 312.5 going up, we're going to need a lot of positive shear fighting it downwards. So we need a lot more of this to fight this point load that we've just encountered. So this means we're going to be going upwards on our shear. Upwards by how much? A 312.5. And since this is a negative 312.5, this gets a V is equal to 0 at x is equal to 3. So we have indeed gotten our V diagram equaling 0 at the end. So that's great. So now we can do our moment. We know from this that the moment is the antiderivative of my shear equation. And I have my two shear equations at play here. So I can do that. And we can do this antiderivative with inverse power rule. Get a negative 150x squared, a plus 737.5x, and of course we'll have a plus c constant. Alright, we can figure out the c no problem because we know at x is equal to 0, our m is equal to 0. So if I plug in a 0 here, a 0 here, and I'm getting a 0 here, that means that doing that math, that c must equal 0 as well. So, this is where the graphing calculator starts getting really handy. This is not a simple line. We know that this is going to be a concave downwards parabola, like this. Remember, this equation is only valid from here to here, just like the shear equation that produced it is only valid from here to here. So only a section of this equation is going to be the one that we actually plot over here. So we can do some complicated Calc 1 magic with curve sketching, and the derivative is the rate of change of the original function and all this. But for starters, I just suggest, hey, just put this into the graphing calculator, let it tell you what it looks like, and then just plop it right here. In the example problems that we do, we'll let it get a little more complicated and show you how to generate that graph without using the graphing calculator. But for now, I would just say put that in your graphing calculator and it'll tell you. So my m is going to look something like that. So apparently for this downwards parabola, we are graphing this section. This is the section that gives us my valid m values for these cuts. So it looks something like this. Of course, we want to know what our ending point is here. Remember, this equation is valid from 0 to that 1.5 value. So here's 1, 2, and 3. Got to be careful. Don't assume that this is a maximum. I'm making it look like this is sort of the local maximum of this M curve. I should maybe draw a little more like that. Of course, don't make it a line, but give it some curvature, but definitely don't make it look like the maximum, because it probably won't be. So again, to figure out this point, all I got to do is plug in 1.5 in for my x, and we'll see what comes out for m. And again, really easy with the graphing calculator, because I can just hit, I have a TI-84, I can just hit trace, 1.5, and I have a 768.75 coming out. Alright, what happens next is a little bit confusing. What are we supposed to do about this? Remember, this is coming from this point load here. Well, remember, the point load, from what we learned, only affects the shear diagram. Point couple moments affect the moment diagram. So this really does absolutely nothing. Nothing here. I don't have a shift down or up because I have no point couple moment being applied here. So my new M equation that I'm about to develop is going to start from this same point, that same 768.75. So we can just keep moving on. My next V equation is this right here. So my new moment equation will be the antiderivative of this negative 312.5. And that's a pretty easy antiderivative. To figure out the C, we know that at x is equal to 1.5, we have an M of 768.75. And doing that math, you'll just get your C as 1,237.5. So this is another line equation with downward slope, and I know that I'm continuing off our point right here. You got to be careful because this M will be valid from here, but then we see that we have this guy. So here's that downwards M right until we hit 2.25, because that's where this instantaneous couple moment is applied. Remember, because of this, we're going to get some shoot up or shoot down. So let me just figure out what this M value is here. That's no problem. I can just plug in 2.25 in for the x and see what we get for M. So at x is equal to 2.25, we learned that our M will equal a 534.375. Alright, and now we got to figure out how this point couple moment is going to affect us. So here is this point couple moment that's being applied here, this 300. And here is my positive internal bending moment. So if I have this being applied at this point right here, I'm going to need a lot less of this counterclockwise M. I'm going to need M in the negative M direction to fight against this. So because I'm going to need more negative bending moment to fight against this, this curve is going to shoot downwards by 300. So I just got to subtract 300 off this to figure out where I end up. Gets me around 234, which will be around here. That's 234.375. Alright, and now we can see what happens for the rest, for our M. Well, notice that my v equation is still this negative 312. So when I do the antiderivative of it, I still get the same equation. The only thing is that our c is going to be different. So really, I have the same exact line as we did before. It's just that this line has been shifted down because of this instantaneous shift. So really, I have the exact same equation as last time, but minus a 300. And if I minus this whole thing by a 300, it's going to take a chunk out of this 1237. So if I do 1237.5 minus 300, that'll get me a 937.5. But again, still the same downward slope line, and this m is going to be valid all the way to the end. But let's just figure out where it is exactly at x is equal to 3. No problem. We'll plug in 3 here and see what we get out for m. And we'll actually get a 0. And now we're going to end up right here. M is equal to 0 at x is equal to 3. And that's great because it checks out with this criteria. So what I have here are the complete equations for each one of my sections. Boom, boom, and boom. And that's how you do it. Now, one final note is that at least the teachers at my school, I think the way they teach is they encourage you really to just graph it without your graphing calculator. And you are able to do that, but it gets a little bit tricky. So I just wanted to show you the most straightforward way of doing it from the get-go. It's a little bit tedious, a lot of graphing calculator calculations to do, but what you end up with is all the information about all of your shear and your bending moment diagrams. So, of course, we'll do some practice in the next couple of videos. Hope this intro video made sense to you. If you have any questions, please post them in the comments.